You ever stop to think about the secret languages that are running our world? Like right now? Well, today, we're going to decode them. From the math behind a simple magic trick, all the way to the code that keeps our entire digital lives safe. So let's just jump right in with a little puzzle. What on earth could a magic trick, a national election, and a top secret message possibly have in common? They seem totally unrelated, right? Well, the answer is actually pretty amazing. They all run on hidden codes. And we're not just talking about spy stuff here. These are the fundamental languages that power our modern world, usually in ways we don't even see. And the most fundamental code, the one that underpins everything else, is the machine's native tongue. It's kind of wild to think that every single computer speaks a language that only has two letters. That language is called binary, or base 2. It's a number system that only uses two symbols, a 0 and a 1. The easiest way to think about it is that every single bit of information inside a computer is just a tiny little switch. If it's off, it's a 0. If it's on, it's a 1. And that simple on-off logic, that's the bedrock of literally all digital hardware. Now, I know it sounds a little strange, but it works just like the number system we use every day. In our regular base 10 world, when we see the number 11, we know it's not two ones, it's 110 plus 1 1. Well, binary is the exact same idea, just using powers of 2 instead of 10. So a number like 1011 in binary, that means we have 1 8, 0 4s, 1 2, and 1 1. You add them up and you get 11. It's the exact same value, just spoken in a different language. And this is the part that is just absolutely mind-blowing. Everything you are looking at on your screen right this second, the words, the pictures, this entire presentation, at its very core, it's all just an incredibly long, perfectly organized string of ones and zeros. That's it. Okay, so now that we get the language, let's see how computers use it to do things that feel like actual magic, like finding a needle in a digital haystack, almost instantly. So imagine you're looking for one specific word in a giant book. You could do what's called a linear search. Start at page 1 and just read every single word. So slow, right? But the smart way to do it is a binary search. You flip open the book right to the middle. Is your word in the first half or the second half? Boom! You just eliminated half the book in one move. You just keep doing that, dividing the problem in half over and over until you land right on the word. The only catch, and it's a big one, the data has to be sorted first, just like a dictionary. This logic is ridiculously powerful for computers. But could that same idea of dividing and conquering actually work with something as low-tech as a simple deck of playing cards? Okay, you've probably seen this, the classic 21 card trick. Someone from the audience secretly picks one card. The magician deals out 21 cards into 3 columns. The volunteer just points to which column has their card. Then the magician picks up the piles, but, and this is the key part, they always put the chosen column right in the middle of the other 2. They do this whole process 2 more times. And here's the secret. It's not sleight of hand, it's just math. Just like binary search uses base 2, this trick uses base 3. Every time the magician puts that chosen pile in the middle, they're physically encoding the card's location. And after you do that 3 times, the math guarantees, the secret card will always be in the 11th position. It's a physical algorithm disguised as a magic trick. Now, this idea of using simple rules to guarantee an outcome isn't just for magic tricks. It has massive, massive implications for something we all rely on, voting. But here's the twist. What happens when the code for a perfectly fair system turns out to be impossible to write? So let's think about what a fair election should look like. We could probably agree on some common sense rules, right? Like first, if literally everyone prefers candidate A over candidate B, then A should definitely win. That makes sense. Second, no dictators. One person shouldn't be able to decide the whole thing. And third, the competition between A and B shouldn't get messed up just because some other candidate, C, is in the race. These all seem totally reasonable. Well, get ready for the bombshell. A Nobel Prize-winning economist, Kenneth Arrow, proved with pure mathematics that if you have an election with 3 or more options, there is no ranked voting system in existence that can satisfy all of those simple, fair rules at the very same time. It's called Arrow's impossibility theorem. And the implication of that is just profound. It means that every single ranked voting system we could ever possibly dream up is guaranteed to have a potential flaw. There's always going to be a trade-off. We can choose which rules are most important to us, but we can never, ever have them all. The hunt for a perfect system isn't just hard, it is mathematically impossible. So if a perfect code for fairness is impossible, what about a perfect code for secrecy? Well, let's dive into the elegant and incredibly powerful language that keeps our entire digital world secure. This magic is done with something called asymmetric cryptography. The whole idea revolves around having not one, but a pair of keys. One of them is your public key. You can share it with the whole world, no problem. But the other one is your private key, and you guard that thing with your life. They're connected mathematically, but you could never figure out one just by looking at the other. Honestly, the best way to get this is the padlock analogy. It's perfect. So imagine you create an open padlock. That's your public key. You make a bunch of copies and you just hand them out to everybody. Now, if your friend wants to send you a secret message, they just put it in a box and snap your public padlock on it. That box is now locked up tight. And here's the cool part. Even though everyone has a copy of your open padlock, the only person in the world who can open it is you, because only you have that unique private key. So what's the mathematical wizardry that makes this all work? It's all based on a really simple but incredibly powerful idea. It's super easy for a computer to take two massive prime numbers and multiply them together. But, and this is the whole secret, it is unbelievably, almost impossibly difficult to take that huge resulting number and work backward to figure out which two original prime numbers made it. That one-way street is what protects your online banking, your private messages, pretty much everything. So, from the ones and zeros that build our screens, to the logic that finds information in a flash, to the paradoxes that shape our choices, and the secrets that keep us safe, our world is, quite literally, built on code. So the only real question left is, what will you decode next?